Hello, this is a video for COMP345. This is for week 9, slide set 8. This is slide set is about design patterns. There's going to be only one video for this slide set. For this semester, we have chosen to actually concentrate on two design patterns at this point because we already saw the observer design pattern earlier. So at this point, I'm going to be talking only about adapter and strategy. So the slide set includes other patterns, but we're going to only cover these two right now. And you only, for example, in the examination, you're only going to be responsible for these. Also, these are two patterns that we will exercise or ask you to exercise in assignment number 3. So let's go to the slides. So first, as I do always when I talk about design patterns, I like to explain what is the notion of design pattern. Now, if you are in software engineering program, probably you've already heard about that. So maybe I'm going to provide you with a different point of view on it. And if you are in computer science, then probably you've never heard about that, hopefully. Not that it's a good thing that you never heard about it, but it would be a good thing that you do. So where does it come from, the notion of design patterns? Well, it has a strange history in its beginning. Actually, it comes from a man named Christopher Alexander, who is actually an architect. He had this outlandish idea from architect's perspective of actually designing some kind of language that he described it as a language, kind of a formal way of describing how you would go and do architecture. The basic idea being that when you do architecture, there are somehow building blocks, there are concepts that have to be, for example, like in a house. Like you have a kitchen. How do you organize a kitchen? What is the pattern of a kitchen? What is the common components of a kitchen, and how should they be organized together? How that it actually is a fully working kitchen, and what would be the ideal way to place a kitchen in a house so that it serves better its function. Okay. So he was describing architecture in this way, and he actually designed some kind of language or model to actually express architectural elements. Now, this was actually done in the late 1970s, which coincided with the emergence of what we call now software engineering. So the software engineers were looking for ways to actually express or represent or think about modularity in software design. And inevitably, some of them came onto this book by Christopher Alexander, which is called A Timeless Way of Building. I actually read this book myself. It's an interesting read. Yes, it talks about architecture, but it's very striking at when he starts describing the language or the model. It's actually kind of a mathematical model that he that he uses to express design. So yes, it's an architecture book, but when you know about software engineering, it's very striking that it's almost like he's talking about software. No, he's talking about architecture. So that's what probably struck the people in software engineering at this point in time, and that's how they somehow used or adopted this notion of design patterns, for which was defined by Christopher Alexander for architecture. They adopted this notion for software design patterns. So that's very often there's a strange evolution or ideas comes from strange places in computer science. In this case, comes from architecture. In, for example, the early days of compilers, then many of the ideas actually came from linguistics, which is a way to actually reason about human languages. So there is very often in the history of computer science and software engineering things that are flowing from very uncommon places that become adopted as practices. So that's it about the history of design patterns. So let's describe how do you describe a design pattern? So, it's very important to understand if you want to study design patterns, it's very important to understand that they all have the same way of describing them. So there's kind of a pattern to describe design patterns. So it's kind of a meta pattern that you use to describe a pattern. So essentially, a pattern has a name. It actually has a problem, a solution, and consequences. So this way of describing patterns was somehow invented in a very famous book nicknamed Gang of Four. I will refer to that later. There is a reference at the end of the slides. It's an extremely famous book that initially describes or described a somehow large set of design patterns. And this book used this way of describing design patterns, and this has somehow been adopted ever since. So why is it a good way to describe design patterns? First of all, it says that a pattern should have a name. Everybody should agree on what's the name of a pattern. When you use patterns, it's basically something that becomes part of your language. So of course, it's very important when you use language that we all agree on what's the meaning of the words that we are using. So if you're using a certain pattern, let's say you said you're using the observer pattern, then we both have to agree as what's the meaning of that. Okay. So that's why there has to be a name, a word associated with this pattern, so that as soon as somebody says this word, then we both agree on what's the meaning of that. Okay. That's why, first of all, it's important to always use the right names and terminology as you're using design patterns and studying them first. Second, a pattern has associated with it a problem. So a design pattern is there to solve a problem. So there has to be a generic problem that this design pattern is solving. And that's what this part of the design pattern description is describing. It's important to understand that the problem is something which is of abstract nature. So as we will see also, the solution is an abstract solution in the sense that it's not a specific problem. The idea of a design pattern is that you want to be able to use it in as many circumstances as possible. Okay, the more a pattern is repeatable across different specific problems, the more it is useful. If it is to be applicable to different problems, it has to be described in an abstract way so that it is applicable in many different specific problems to solve many specific problems. So you have to describe what is this problem that this pattern solves, and it hopefully has to be described in a very abstract way. One of the goals of describing the problem is to be able to identify when you have in your own design problem that you have right now in your development, you have to be, as you see the problem you have to be able to say easily, somehow, this problem I have here can be solved using this specific pattern here, because basically this is the same problem. The specific problem here I'm having is the same problem as this abstract problem that this pattern is describing. So that's how you map somehow. You come to realize that to solve this problem, I will adopt this pattern because it's the same problem. So very often a problem would be described in terms of different conditions that must be there for a certain pattern to apply. Then, of course, the pattern is a solution, so the solution should be described. Now, the solution, well, in the slides, you will see that I'm giving specific examples of the application of a pattern. You should not think that this is the solution. This is just one example of how this pattern can be used to solve a specific problem. Solution part of a pattern is always described in a very abstract way so that it can be usable in different specific ways or to solve different specific problems. One of the difficulties with the description of the solution of a pattern is it uses very often would use very specific terminology. Okay, so you have to come to know what is the terminology, because if you discuss with people, again, it's important that you use all the same words to refer to the same things. So when you study design patterns, it's important to study also the terminology. So for example, there's a class, for example, in the observer pattern, there was a subject and observer. So these are two terms that you should use when you describe or define a pattern in your implementation. So yeah, so solution, again, always an abstract description of the solution to the problem, to the abstract problem. Important to realize also is that there's very often consequences of applying a pattern. In general, when you apply a design pattern, it actually is proposing that you add some classes to solve parts of the problem. Now, that makes it so that probably, arguably in all cases, if you apply a design pattern to solve a solution, you are probably going to use more classes and more objects than if you're not using this pattern. So that's one of the most common consequences of applying patterns. Now, if the problem that you are trying to solve requires extreme efficiency and, lean memory usage, then probably you don't want to use design patterns. Okay, so you have to, there's very often some um, trade-offs between different requirements. Okay, so if modularity is very important for in order to have better maintainability, then probably it's good to use design patterns because they are good to achieve that. However, if efficiency and low memory consumption is your main requirement, then you probably don't want to use design patterns. Okay. So you have always to be aware of what are the consequences. There are limitations that are brought by the specific pattern. So it's important to know them. I noted here that a common consequence of all patterns is probably increased memory consumption, but each specific pattern has their own specific consequences. This is, I mentioned just one that is common to all of them. So this is the book that is very famous for having popularized, I might say, the notion of design patterns. So it's essentially a book that goes and describes pattern after pattern after pattern. It's kind of a dictionary somehow of patterns and examples of using them. Okay. So there are like dozens of different patterns. And this book had introduced 23 of them. Since then, there are many that were invented. Many are variations of the original ones. So it's important to know what are the original ones and what are some variations. You want to learn the basics before. There's no point in learning all the different patterns. Okay, it's better to actually know the ones that are used most often and then know them well. Okay. So in this course, we've covered the observer pattern earlier. And then here, we're going to cover only the adapter and strategy pattern. So let's go to directly to the slide for, I believe it's 37, am I right? Yes. So let's go and see the adapter pattern. So what is the observer pattern? Why would you want to use an an adapter pattern? So of course, when you hear the word adapter, you, if you have a laptop, then you know that your laptop has an adapter. Almost every electrical device has an adapter. What's an adapter? It's basically that your device, for example, uses 5 volts, whereas the electricity that you have in your house is 120 volts. If you would plug your device directly into the wall, it would cease to work. Okay, so there needs to be some translation, essentially, of the electricity from what is provided in your house to what is needed by your device. That's why you need an adapter. So software adapter design pattern is exactly the same idea. You have something that is provided already, that you know how to use it, and you always use it as it is. But then comes this new thing that you have in your hand here. It does not use the same interface, literally. Okay, this uses 5 volts. This provides 12 volts. This is not the same requirement. Okay, so you need somehow a translator that would translate 120 into 5. Okay, so that's what is the notion of an adapter. So most specifically here, what you want is to convert the interface of a class into another interface that the client class expects. You see, the client is one of those terms that is used by design patterns. Client does not mean the person you are delivering software for. Client means a client class, which is the class that is using a certain feature. Okay. There's lots of terms like this that I use when discussing about design patterns and defining them. So the adapter, so you'll design a new class, which is called the adapter, that will let these two classes work together. So you can imagine that this electricity you have in your wall is one of your classes, and then this new device you have, they both use electricity, but you need to make them work together. So you're going to design another component that is going to do the bridge between the two. Well, probably bridge is not a good term because there's another pattern. It's called bridge pattern. So you see, you have to be careful when you design, when you talk about design patterns and the terms that you are using. Okay, so you have the client code here. So this is the code that is actually using a certain component that you already have. Okay, so this client code is using a certain class. Let's call it the target class. That's the term that is used by the adapter pattern for this component. So you see, it's a very abstract kind of term, the client and the target. Particularity of this target is it has a method, for example, named request. Okay, so the code here always uses this piece of code here and then calls request from this class, which is of type target. Now, the idea here is that, for example, you may want to change this code so that it uses another class. So here comes another class which provides you with some kind of variation of what this target class is already providing to you. And there's a reason why you might want to use this other class. But there's no relationship between this other class and this class you already have. There's no relationship between the target and the adaptee, which is this the abstract name for this other class that you want to use now in your design. Another assumption of the adapter is that you cannot change the target or the adaptee. For example, you cannot make the adaptee a subclass of target. You cannot change the method name here in adaptee to the same name as this. the assumption is that you can't change anything about this class nor this class. Okay, so you see there's an assumption here. If you could, if you would be able to actually change the code of either the target or the adaptee, then this problem would not be there. Okay, so the assumption is that yes, you have this class, you want to use another class, there's no relationship between these two classes, and you can't change either of these two classes. What do you do? Of course, the other assumption is that the target class and the adaptee class are providing somehow the same service in a different way. And the new one is more desirable in some case, probably, than what you already have. So you want to use it. So what do you do? So the adapter pattern says you essentially design a new class called the adapter that is going to be a subclass of your target class. And then it's going to contain a data member of type adaptee. So, and then it's going to provide or override the function request from the target class that it inherits from. So that eventually, as the client will use this class that implements request, it would rather use an adapter, which is also of type target. So from the client's perspective, it's still using an object of type target because adapter is also of type target. And it's still using the request method of the target, the object of type target. Now, what does this request method do? As I said, inside of the adapter here, there's an object of type adaptee. And then this object of type adaptee as a data member here resides inside of the adapter. And what the request method does, it essentially delegates the call to request into a call to specific request of the object that is inside of adapter, which is the adaptee. So you see that here, I made a bridge between these two things. I allowed the client to actually use an adaptee without it even have to change its own code, except that, of course, it has to declare an object of type adapter, but it still uses it as an object of type target using the same method call and so on and so forth. So here, this uses a, I might say, a micro pattern or something that you see very often happening in a lot of different patterns, that you create a new class that is a subclass of something you already have. And then inside of this new class you've created, you insert an object of another kind, and then you provide a method that delegates to the object that is inside of the new class you've created. This is a micro pattern, repeats itself in a lot of different design patterns. So when do you use this adapter pattern? So essentially when you have a client class that invokes methods define a certain target, and you have another class, the adaptee, that doesn't implement the same interface, but it provides the same service through a different method name. Note that it's also possible in the example here. This is a simplistic example. But very often when you see examples about design patterns, they are simplistic examples. Here, for example, in this example, the delegation here, when you call request, what it does is actually directly call adaptee.specific request. Now, it's possible that that's not as simple as that. Maybe for example, specific request is returning a type that is not known to your design here, in which case the adapter would have to somehow make some translation and translate the return type that is returned by this function into the return type that is actually returned by this function here. It's possible that there's some translation work that has to be done as part of this overriding request method here. Okay. Of course, as I explained earlier, the assumption in the adapter pattern is that you cannot change any of the adapter or adaptee code. Okay, so the solution is only to add a new class in the middle without changing any of the existing classes. So let's see an example. So this is that the examples I give are always typical examples. If you look on the internet, you'll find similar, I would say, similar examples. I adapted typical examples for the course. So this is essentially the square hole, round hole example. So you have two different kinds of pegs. So this is kind of a woodworking analogy here. So you have two pieces of wood. You want to insert a piece of wood into the other piece of wood. So either you have a round peg and you have to do a round hole to insert the piece of wood into the round piece of wood into the round hole. Or you have a square peg piece of wood, and then you want to insert it, in which case you have to do a square hole. Now, what if you have a square hole and then you have a round peg? How can you make it so that you can somehow join these two pieces of wood together without changing the two pieces of wood that you have? Okay, so you see that it's not about I'm going to make this square peg round. I'm going to machine the square peg into a round peg. No, you want to keep square peg and a round hole, and then somehow design a solution that allows you to join these two pieces together. Of course, that would involve that you design a new piece of wood in which you're going to insert the square peg, and then you're going to design this adapter essentially is going to adapt a square peg into a round hole. So you're going to have an additional piece of wood that allows you to join the two pieces together. So you have square pegs and round pegs. So in terms of software here, of course, this is our two classes which have two different names. They are totally unrelated to one another. Okay, round peg is not a subclass of peg, and square peg is not a subclass of peg. They are not subclasses of each other. No, it's absolutely, even though they are named both peg, they are unrelated classes. Okay. And they also have a method that is of different name. Okay, so your client code here is probably used to use a square peg and then to call insert into square hole. Okay, so what you want is to be able to use a round peg in place of a square peg without changing either of square peg and round peg. So solution is you design this adapter. So this adapter class, I remind you, this is the adapter that you have here. This is the adapter you have here. So it has to be, and this is my round peg here, and this is my square peg. So I want to make my adapter a subclass of my round peg. Or sorry, square peg. So my target is the square peg. This is the adapter, and my adaptee is the round peg. Okay, so you see that it's important to know what is the terminology here. Okay, if you want to discuss with your teammates about how you implement that, it's important to use the same terminology. So this is the adapter, this is the target, and this is the adaptee. So the adapter inherits from the target and then contains a data member which is of the type of the adaptee class. Then what it does, it implements or overrides the insert into square hole method of the target class. What this new method does is essentially delegates when you call insert into square hole of adapter, which is a square peg, what it does is calls insert into round hole of the round peg that's inside of it. Okay, but this delegate subclassing and then delegation is very common that you have that in many different patterns. We will see that also in the strategy pattern, a variation of this pattern, this micro pattern, I might call it. Okay, so this adapter, this is the this adapter class. This is the adapter in terms of the abstract terminology. This is the target. This is the adaptee. This is the method that overrides the method that is inherited from square peg, which has the same name. So when you call it, what it does is it delegates this call to the round peg object in its own method name. Okay. Again, I repeat here, it's possible. This is a simplistic example. It's basically only delegating. It returns the same type and so on. Not necessarily the case in real life. Okay. There might be some translation work here that needs to be done. Might even be possible that a single call here would result in a series of call in the adaptee. Okay. So don't think that it's always as simple as that in real life. So how do you use that? So here I have my main function. By the way, this code is available on the material for lab number 8. That's my main function. So I see here I create a round peg and a square peg, or pointer to round peg and square peg. And then here I'm calling insert into square hole of the square peg. That's what I used to be able to do as the client code. Okay. That's what I was doing before I had this notion of round peg discovered. Okay. Then what I do here is I'm showing that I can actually use a round peg. So here I'm going to create the square peg to round peg adapter, and I'm going to feed a round peg to it. One thing I didn't mention here is that my constructor here receives a round peg, and what it does is it assigns this round peg that it receives as the instance of this data member here that's inside, which is of type round peg. That's why when I call this here, it creates an adapter, which is a square peg, because it's a subclass of it. And then I'm actually able to use this adapter by calling insert into square hole, even though here I'm eventually using a round peg. Okay. So that's how I would use the adapter. That's not really interesting. Where it comes interesting is, for example, I could have a variable of type square peg, or let's say here an array of 2 square pegs. One which is a real square peg, and the other one which is a square peg, because it's an adapter, peg adapter, which is of type square peg, which of course is using this adapter and then contains a round peg. So I'm going to show here that I can use both of these here using exactly the same code. For example, I can go square pegs of 0, insert into square hole. That's of course calling this insert into square hole of the square peg that I have here. But I can also use pegs 1, insert into square hole, because the adapter provides this method which delegates to this round peg that's inside here, that's been inserted here in the adapter. So here I show that I can use both of these square pegs as a square peg, even though one of them is actually not a square peg. Okay, so that's the example about the adapter pattern. So it's important that you realize that, I was describing adapter, adaptee, target, client, and so on. This is the solution of the pattern. This here is not the solution. It's an example of application of the pattern. Okay. it's important you make the difference between the two. If you want to study design patterns, you should study the abstract solution, not the concrete example that is used to exemplify the application of a pattern. So yes, this is not the solution. This is an example of application. Then, so that was the original adapter pattern. Then the question becomes, because very often for patterns, there is some questions after, what if I want to have X, which is more than what the classic adapter is providing? In this case, for example, what if I want to have an adapter that works in both ways? Okay. A square peg, a round peg to square peg, as well as a square peg to round peg. Okay. So that would be called a two-way adapter. That's a variation of the classic adapter pattern. Okay, so you can't say, for example, the two-way adapter is the adapter pattern. Okay, it's a variation of the classic adapter pattern. Now it starts with the same assumptions, of course. You have square peg and you have round peg. Very good. This is actually a very good example of a good use of multiple inheritance in C++. That's partly why I've introduced this example here. So you have square peg and you have round peg. So basically what we had, if we had a one-way adapter, a classic adapter, we would say we design an adapter that translates somehow a round peg into a square peg. Okay. We want to have, and then we said adapter should be a subclass of the target, which is the square peg. In this case, we want to have both. So what we do is we make this adapter to two-way peg adapter being a subclass of both square peg and round peg so that it can act in both ways. Okay. Then also what we do is inside of the adapter, we have both a round peg and a square peg object. Depending on which way the adapter is currently used, it would either contain a round peg or a square peg. Okay. But still would be a subclass of both of square peg and round peg. Of course, then the problem becomes that if it's used in one of the ways, then trying to use it in the other way as it's currently being used in the other way around is going to lead to problems. Because if I'm creating a two-way peg adapter and I pass it a round peg, it's actually indicating that I want to have a round to square peg adapter. So then I'm going to take this round peg and then assign it to this pointer here. And then the square peg pointer is going to be null. Of course, that's going to create a problem if I'm trying to actually use it the other way around, as it's now connected in the other way. That's one of the consequences, adverse consequences of this variation to the adapter pattern. It would misbehave if you connect it in one way and then you're trying to use it somehow the other way, it's going to hit a null pointer. Okay, then if it is a round peg, or if it is a square peg to round peg adapter, then I want to be able to have insert into round hole, which is then gonna delegate to insert into square hole. And then I have also the other way around. Okay. So this way, depending on which way I'm using, then I'm going to be able to use this particular way of adapter way, right? So essentially, this is doing exactly the same as the classic adapter, except that it provides both ways using the same pattern, and especially important here, using multiple inheritance. Now we can see that if I have round peg and square peg objects, and then I'm creating my array of square pegs, I can have a square peg and I can have an adapted round peg into a square peg. Then I can actually call insert into square hole of both of these things here. This one would be delegating to insert into round hole of the round peg that I put inside of my adapter here. And I can actually do the other way around by having an array of round pegs, pointers to round pegs, and then doing it the other way around. So you see here that very easily, using multiple inheritance, you can have a two-way adapter. So that's it for the adapter pattern. We will require that you use the adapter pattern in assignment number 3 of the project. Then let's go to the other thing we'll be asking you to do in the project in assignment number 3, which is the strategy pattern. So as you may have hoped, so that you're implementing this Warzone game, and then the players, you might think that you want to have different behaviors for your players. That's what the strategy will enable you to do in assignment number 3. So you can define different style of players. For example, an aggressive player, a passive player, a human player, or that's basically what we're going to be asking you to implement using the strategy pattern. So what is the strategy pattern? So again, here, starting with the abstract description of what is the pattern. So motivation of the strategy, sometimes you want to change the behavior of an object depending on some condition that happens at runtime. Now, that's not necessarily easy to achieve. One good way to achieve that is actually use the strategy pattern. So the idea is that you want to change behavior as the program is running. You don't want to change behavior according to having different subclasses and then instantiate with different subclasses depending on certain situations. For example, for the project, you might say, okay, I'm going to have a passive player and an aggressive player. So when you start, then you might say, I'm going to have a subclass of passive player and another subclass aggressive player. Now, that's fine, but what if you want to be able to change the behavior of a player dynamically at runtime? For example, let's say you have a passive player, and then the passive player, you would say, if my behavior of the passive player is if he gets attacked, then would become an aggressive player. Now, how are you going to do that if this player was of a subtype passive player and now he has to become another type? Okay. The strategy pattern enables you to make some changes like this without changing the types of the objects, which is, as we saw earlier, very tricky. So you want to change statically, dynamically at runtime, the behavior of an object. That's the motivation of the main problem you want to solve by using strategy. The intent is you define a group of algorithms that apply to a family of classes. So in our case, in the project, we have a player. That's only one class, but the pattern also applies to if you would have a class hierarchy. And then the group of algorithms would be, for example, how does an aggressive player decide where to attack and where to defend? What cards is the player playing? For example, you might argue an aggressive player might use bomb, but the passive player would never use bomb. Okay, so how do you make that separate from one another somehow, and then assign specific behavior dynamically at runtime? the strategy pattern allows you that. So these algorithms here is in our game is going to be the decision making. Depending on what kind of player you are, you're going to make different decisions. Then each of these algorithms will be encapsulated separately. So essentially we'll design a strategy object that is going to contain all the code about these varying decision making. So you're going to have all the code for the aggressive player, and then all the code for the passive player, and all the code for your human player. And then you make these code that you've designed separately to be modular, and so that you're able to dynamically change the application of this code at runtime. Okay. So what's the consequence of this strategy pattern? It lets a specific algorithm implemented by a method vary without affecting the clients that use it. So you will have you already have a player class. By using the strategy pattern, you will have to change 0 things in your player class. Okay. That's one of the advantages of using the strategy. Now, here's the solution to this problem. Again, here it uses own specific terminology. So here's the client. The client is essentially the code that uses the class that you want to have dynamically changeable behavior. Okay. In your case, that would be, for example, the game engine. Game engine is the client that uses a player. And in our case, the context. Context is the object. Abstractly speaking, the context is the object which has this dynamically varying behavior. Okay. In our case, that's going to be the player. You see that, okay, let's go to the strategy. So here you have a superclass strategy that implements some methods. This strategy can be an abstract class, not necessarily, but it can be an abstract class. Then for each of the different kinds of behaviors, then you have a subclass of strategy. For example, here you would have player strategy in our case, and then you would have aggressive strategy, and then passive strategy, and then human strategy that would each implement decision making that is different according to what kind of player they are. Then you see that the context actually contains a strategy object. So the player will contain a strategy object. Then when you set up an object, when you create an object of type context, then you assign to it a strategy through the constructor. Okay. The context object should always have a strategy from the start. And you can also change this strategy after it had been assigned at a creation time by using the set strategy method that is essentially changing the strategy of the object, the context object. Very important also is that this object here, it has some methods that actually define their own the way that the client is actually using them, in order to, assuming that they have a certain behavior. Okay, so the client would be using this object here in these different ways here. Okay. For example, there could be creation of orders for the player. You ask the player to actually create a new order and place it in their order list. Now, depending on what kind of player they are, if they are passive or aggressive, they will create different kinds of orders. So the game engine needs to be able to tell the player, for example, create a new order. Okay. And that's these methods here, you may have guessed it, that will actually delegate to the actual behavior that is implemented in this class here. Okay. So you see it's the same micro pattern as we saw in the adapter. You create a class that is actually containing an object of another unrelated kind. And then the methods that you have here actually delegate to this object here, thus calling the methods inside here. Okay. That's again this delegation idea that is in many different patterns. So that's what is the general solution of the strategy. So I already explained that here, so I'm not going to repeat that. So you have the context object. That's the object that the class that you want to have dynamically varying behavior. Okay. You assign this behavior from the start. You can change this behavior as it executes by using set strategy. And then it has some methods that the client class can actually use. Eventually, that will delegate to the strategy object that it contains. Then you must have a strategy class, which is the superclass of all the subclasses of strategy, which are specific and different behaviors that you want to implement. The strategy class can be abstract, but it's possible also that there is a common behavior to all of the strategies. If there is such common behavior, then you may want to put some of the method inside of the strategy to implement the common behavior. So strategy class does not need to be an abstract class, but in many cases it is. Here's a very specific example. This is, you might recall the calculator example. And when I described function pointers, this is kind of the same idea here. So my calculator here can actually either add or multiply or divide or subtract numbers. Okay. So the way that it is actually calling each of these different functions in time is by using a strategy. So if I set my calculator's strategy as, for example, divide, then when I call execute strategy of my calculator, execute strategy is going to actually call execute of the strategy object that is here. So if I want to actually have a divide calculator, then I'm going to set the strategy to divide. Okay, the divide strategy. Of course, when I create this, initially this calculator, I should provide with the initial strategy, which is provided as a parameter here. But any point in time later on, I can actually change the operation that my calculator can do. Of course, this is a very primitive calculator here. You would have figured that out. And then there's this method that the client, or the main method in our case, will be able to call in order to use the calculator to do a mathematical operation. And then what it does, it just very simply delegates to the execute method of the strategy that it contains, that its class contains. Then I implement my strategy here. It's not an abstract class or yes, it is. In this case, it is. Sorry, it's in this case it is an abstract class. So my execute method here, there's no such thing as the generic execute method. Okay, it has to be one of the specific. That's why in this case I made it an abstract class. Again, I repeat, does not need to be an abstract class. In some cases, it can be that it may be required to be not an abstract class, especially if you have common behavior across all of these here. Or that you have, for example, a default strategy that you may want this one to be, for example. Okay, so then here I design subclasses of strategy, the add strategy, subtract, and multiply strategy. What they do is basically they implement this execute method, and then very simply returns either addition, subtraction, or multiplication. Okay. So then when I want to use it, create my calculator, and then I create my strategy here and feed it to the calculator. Now the calculator is an add calculator. Then if I call execute strategy of my calculator, it actually multiplies 3 by 4 and returns the result here. Then if I set the strategy of my calculator to subtract by creating a subtract object, which contains an execute method that is implementing subtraction, then suddenly when I call when I set strategy here, and then set strategy is actually changing the strategy object here. So after I've called set strategy, suddenly this calculator is not the same calculator as it was. It doesn't have the same behavior as it had. So you see, I can just dynamically change the behavior of my object without changing its type. I change somehow the type of the strategy object that is contained inside of my calculator, but I did not change the type of calculator. Then after I've set my strategy to subtract, then when I execute strategy in exactly the same way here, it suddenly does a subtraction of 3 and 4. Then I can change to multiply, and then suddenly when I call execute strategy in exactly the same way here, it's doing a multiplication. Okay. So you see that this pattern somehow very simply allows you to create an object whose behavior can change very easily at runtime. So we're going to ask you to do in assignment number 3 to use a strategy pattern to implement different kinds of player behavior. So that's it for this lecture. Thank you.